Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to use the policy gradient method again for continuous mountain car, but this time we are going to actually use gradient descent. So if you don't want to try to code this yourself, the relevant file in the course repo is pgtheano.py in the mountain car folder. So one thing you'll notice is that the structure of this file is very similar to the random version. In fact, the architecture of the model is exactly the same. It's just the way we are training them is different. So at the top we have a function to help us do atom optimization in Theano. This is already pre-built into TensorFlow, so we didn't have to code it manually before, but in Theano we do. This just uses all of TensorFlow's default parameter settings. Encapsulating these now makes our later code a little cleaner since we'll be using atom for both the policy model and the value model. Next we have our hidden layer class, which is exactly the same as before. So let's scroll down. Next we have the policy model class, which models pi of a given s. It takes in an array for the hidden layer sizes, although for our purposes, this will just be an empty array since we'll be using RBF kernels and a linear layer on top. After we create the hidden layers, we create a final layer to output a mean and a final layer to output a variance. Note that the activation function for the variance is soft plus to ensure that it's always positive. Next, we create placeholders for the data. So we have X, which represents the input states, actions, which is a 1D array of actions we took in those states, and advantages, which is another 1D array that we'll be calculating externally. Next, we can pass X through the hidden layers to get the second last layer value, and then put that through the final mean layer and the final variance layer to get the parameters of our Gaussian distribution. We also add a little bit of smoothing to the variance, which is common when you're dealing with Gaussians. And because neural networks always deal with two-dimensional data, we have to convert the means and variances back to 1D arrays using the flatten function. From here, we can define a function for the log PDF of a Gaussian, given the selected actions, corresponding means, and corresponding variances. We also have a function for the entropy of a Gaussian, which only depends on the variance. Next, we calculate the log probabilities using the log PDF function we just wrote. Also note that we regularize our costs by adding a constant times the entropy of the Gaussians. By trying to increase the entropy, what we're saying is that we want a larger variance. This does something similar to the variance smoothing you saw earlier. Finally, we compile the train and predict functions so we can use them later. Next, we have our usual partial fit function, which does one iteration of gradient descent. After that, we have our predict function and sample action function, which just gives us an action from the current policy. Note that our predict function is actually going to return a tuple of arrays. The first item in the tuple is an array of means of size 1, so that's indexed by 0, 0. The second item in the tuple is an array of variances of size 1, so that's indexed by 1, 0. This is because we'll only ever be sampling one action at a time. Next, we generate a sample from a Gaussian with this mean and variance. An easy way to do this is just to sample from the standard normal and then scale and shift it by the standard deviation and mean. We then clip the value to be between -1 and +1, since the environment won't accept actions outside this range. Next, we have our value model class. Unlike the random hill climbing script, we need to model the value as well, because that's used in our calculation of the advantages, which is ultimately used to calculate the policy objective. This is opposed to the hill climbing situation, where all we did was parameterize the policy and then pick the policy that gave us the best reward. So this is very similar in structure to the policy model. We have a number of hidden layers, and then a final linear regression layer to predict the value. Nothing much new in here. We use the squared error for our costs and minimize it using Atom. Next, we have our partial fit and predict functions. So this is pretty much the same as the policy model. Next, we have the play1td function. This loops until we get the done signal or until the number of iterations hits a maximum threshold. So depending on your version of Gym, it may cap off at 200, but I found that to be too small to really learn the environment. So if you have an earlier version of Gym, it's probably better. Inside the loop, we select an action from our policy model, do the action, get the next state, and then update both of our models with one iteration of gradient descent. Next, we have our main function. This uses the same RBF feature transformer from earlier with 100 components, and we're using shallow networks in this script. So just linear layers on top of the RBF feature expansion. Next, we play 50 episodes, plot the rewards, plot the smooth rewards. Of course, you can use a different window size since we aren't playing that many episodes. And then lastly, we plot the cost to go function. You're looking for the same hill shape as we've seen previously, although I found that these hyperparameter settings to be somewhat inconsistent. So let's run this and see what we get.